Okay, so this is the midterm one for plane trigonometry. Uh, so problem one. Well, we have a paragraph that describes this diagram. So I'm just going to refer to the diagram. We have the angle, 70 degrees. It's a right triangle. The wall height is 30 feet. And we want to figure out the length of the ladder and round to the nearest, typo, round to the nearest 0.1 feet. Maybe I can mark that. Right, so in order to figure out the length of this side of the triangle, well, we have this angle, we have this side, and, well, this side is the opposite side to this angle, and this would be the hypotenuse. So we have to think what trig function relates the opposite side and the hypotenuse, and that's going to be sine. So we know that sine of theta is opposite over hypotenuse. And so we can then set up the equation. I don't like the thickness. We will end up with the equation sine of 70 degrees is equal to 30 feet over the length of the hypotenuse. Yeah, I can just write it as the hypotenuse. Okay, so now we've set this equation up for the specific problem that we're given, and I can solve for the variable that we're looking for, which is the hypotenuse. So that's going to give me 30 feet divided by sine of 70 degrees. The units here aren't really important to write, I'm just sort of writing them. What we will know is, though, that the output of this, it's going to be a length, and so we know that whatever value we end up with, it's going to be measured in terms of feet. You can kind of see that here. That's in a way why this feet, I'm kind of propagating this along. And here I have on my right-hand side a calculator. So let's just go ahead and compute this sine of 70, and I want to double check also that yes, my calculator is set to degree mode. I do have the ability to switch the settings for that in here. This is Speed Crunch. It's an open source program, free open source. You can use it if you want to. You could just use whatever calculator you prefer, as long as you understand all the, I guess, as long as you know how to use it, right? As long as you know the functionalities of it, it's fine. Okay, so let's see. It's 30 divided by sine of 70 degrees. This is, there's a lot of values there, and we want to round to the nearest 0.01. So that's going to end up being approximately 31.93. So you notice that I do have to mention rounding because I actually saw some people round incorrectly. I think they just truncated. But you see the 5 there, right, tells me that this 2 gets rounded up to a 3. Right, so this is actually 31.93 feet. I need to put down feet here. And I guess I can box this. I wonder if this is going to work. Ooh, nice. Yeah. Okay. So that's number 1. Number 2, we have a triangle whose angle A is this, angle B is this. So we want to find angle C, and we want the answer phrased in the degrees, minutes, seconds. Okay, and it's giving us a little hint that the 3 angles in a triangle add up to 180 degrees. So if you didn't know that, well, that's a very useful thing to know, because that's how we're going to solve this. So there's sort of 2 ways you could do this. You could take 180 degrees, subtract off A, and then subtract off B. Or you could add A and B together, and then do 180 minus their sum. And I think that the second approach that I have said is kind of the more natural thing to go about doing. So what we're going to do is we're going to add a plus b. Okay. So we're going to do that calculation first, and then we're going to subtract one. We're going to do 180 minus that. Right. So we set this up in sort of a columnar format. So that's A, B is this. Don't really need to put the markings there. That's fine. But then we're going to add these. Well, we should go right to left, right? So this is 65. This is 80. And this is 106. Okay, so we have something. But now if you look at this, you should recognize that this is a bit weird because 65 seconds, 80 minutes, these are kind of larger than they should be. Because you should remember that there are 60 seconds in a minute, and there are 60 minutes in a degree. So by going over 60, it's like we've kind of exceeded the natural amount of stuff in that kind of unit of measure. It's kind of like exceeding inches. If you said like 34 inches instead of something in feet and then inches, so that's like what, 2 feet 10 inches, I think, because it's 36 minus yeah, it's 2 less than 3 feet, so it's this is the same as 2 feet and 10 inches, that kind of thing, right? Maybe I'll just comment that 2 inches is usually with double comma, isn't it? I don't remember. I don't use no units. I don't do real world things. Okay, whatever. Yeah, so it'll just be useful for us to kind of get rid of these excesses in the units. So this 60 is going to propagate over here, and it's going to increase this by 1. So maybe I'll do this one bit at a time. So this will give me 5 seconds. I'd like to put this extra 0 just kind of as a placeholder. Okay, so this is the same thing. I'm just kind of pushing things forward. And then 81 is also, it has exceeded 60. So we kind of want to turn the 60 minutes into a degree. So this will give me 107 degrees. And we're going to have then 21 left over, just subtracting 60 from 81. So this is kind of the simplified form of a plus b. Okay, so we got that. We got a plus b. And then what we need to do now is 180 degrees minus this quantity. All right. So yeah, the plan was that c is 180 degrees minus this sum a plus b. Okay. So now what we need to do is subtract. So we do 180 degrees. And I'm gonna add these extra columns. Right, so 107, 21, 05. Okay, and we're gonna subtract this time. Now we can't do 0, 0 minus 0, 5, so we need to bring the values down. So I'm gonna turn this to 79, and then if we did this in stages, we were sort of transforming 1 degree into 60 minutes, but then we're going to end up propagating that along as well, because we need to go all the way down to here. So we take one of those minutes, and we, maybe I'll just erase this also, I don't need that. So we take one of those minutes, and we then convert that into 60 degrees. So we end up having this. So instead of working with 180, 0, 0, we are now working with 179, 59, 60. Okay, maybe I should also put that extra 1 there. That's good. Okay, so now we do subtraction. 60 minus 5, that's 55 seconds. 59 minus 21, that's 38 minutes. And then 179 minus 107, that's 72 degrees. I'm just going to also double check my arithmetic. Yeah, looks good. Okay. I'm going to box that as well. Maybe I can use a color box. All right, nice. Okay. Number 3, we are doing conversions to this DMS format. Okay. So 138.785 degrees. Well, the process that we do this is we take the decimal part and we kind of convert that over. So think of it as like we have an integer part and then we have a fractional part. Okay, and then the fractional part, or this decimal part, that's what we end up multiplying by 60 to convert it. So when I take this, and this is measured in degrees right now, if I multiply it by 60 minutes, that's going to be a unit conversion. It's going to give me the value of that angle, but in minutes instead of in degrees. So we're just going to type that in, 0.785 times 60. And, okay, so I don't like this format. Let me just fix this. Behavior, no, wait, no, this, decimal, fixed decimal, scientific, general. Let's do general. Okay, yeah, that extra exponential thing at the end, probably not good. Okay, so this gave me 47.1. Let's just say what that is, 40. Oh no. So this is 47.1. 47.1 minutes. Okay, well, we have an integer part, which is the 47, and then we have a fractional part, which is the 0.1. So really, we're viewing this as a 47 minutes plus a 0.1 minutes. And then this 0.1, we're going to want to convert. So this guy, we're going to multiply it by 60 seconds. That's going to convert me from minutes to seconds. And, well, this guy, I don't need to, use a calculator for that. That's just going to be 6. Right. So all in all, the answer for this is going to be 138 degrees, 47 minutes, and I'm adding an extra 0, 6 seconds. Yes, that's correct. Okay, let me box this. Computers. Okay, great. Whatever. Okay, now we have this radians, this measure in radians that we want to convert to DMS. The thing is, well, we know that the procedure for doing this is we convert from radians to degrees, and then we go from degrees to DMS. The conversion to get to degrees, let's set this up. So right now this is in radians. The conversion factor is going to be 180 degrees over pi radians. Right, so this will convert me over, and I can at least cancel the pi. I can probably cancel more. Let's see how 3240 divides with 180. Okay, 18, great. So that ends up being an 18 in the denominator. Right, so I can actually write this as 427 over 18 degrees. And I'm pretty sure that 427 doesn't really simplify. So this calculator doesn't have the ability to just simplify fractions, but I can try to. This 427 is odd, so it doesn't divide 2. I can try to divide by 3. I get a decimal, so it doesn't divide 3 evenly, and there's no other prime factors for 18. So yeah, I'm pretty sure this is the simplified fraction form. Okay. Now, to convert this to DMS, it would be nice to see the decimal representation. So let's just do 427 divided by 18. Okay, so we have a fractional part, which is, we have the integer part, which is 23 degrees. We have the fractional part, which is 7 to 2 repeating degrees. So there's a couple ways. There's two ways to go about this, I guess. One where you're working with the decimal version, but you're being careful with the precision. And then there's the other way of working with this, where you're working with the fractions. Maybe we can try doing either way, and then you can choose which way you're more comfortable with doing it. So, all right. So looking at this in terms of the decimals, so what's important is, and I hope this notation makes sense. I'm just gonna say, okay. So the bar on top of the numbers represents the pattern that is repeated. So this means that the 2 is repeated infinitely. Yeah. So if you were to use your calculator, what you should do is either hit a bunch of 2s, maybe like 3 or 4 2s, just to make sure your precision sticks around. Or you can refer back to your previous calculation using like some answer key. Usually these scientific calculators, graphing calculators, they should have some way to refer to your previously computed result, some answer key, and you should just be able to hit that thing to then retrieve the value. All right, so I'm trying to do the decimal version. Okay, so we have 23, and we can do the same process as above. So we can split this into the 23 degrees plus the 0.72 bar degrees, which we would multiply by 60 minutes. And this guy is going to give me, and on the calculator, one way to do this is to just subtract off the 23. So now we have the fractional part that we then multiply by 60. Yeah, and on this calculator, you see that ants is it's a variable name actually that gets me that uses the previous calculation. Okay, right. So this is 43.3 repeating minutes, and well, we can split that. So 43 minutes plus this 0.3 repeating minutes, which we would then multiply by 60 to convert it to seconds. Okay, and on the calculator, we subtract off the 43 so that we are working with the fractional part. We multiply by 60 so that we're working with the decimal part. Okay, so then this part is 20 seconds. That's what we've done. We've converted from minutes to seconds. Yeah. Great. So then combining all of this together, we've found that the answer is 23 degrees, 43 minutes, and 20 seconds. Okay. All right. Oops. The other, I can try to fix this. I don't want it to snap to grid. I have no idea how to fix that. Oh well. Yeah, no idea. Okay. The other way, just in case anyone prefers it, is going to be. Let me try to. Oh, I want to divide the space. Okay, that's not what I mean. Try to just. Oh no. All right, that should be enough. Okay. So we would. The idea is we need to calculate what this fraction is. We're converting it from an improper fraction, which is how it is right now. The numerator is bigger than the denominator. We convert that to the mixed fraction notation. So looking at this decimal representation, that tells me that you have 23 whole parts, and then you've got some fraction that's left over. So what we know right now is that this is 23 plus something over 18. And our goal is to figure out what is this numerator. So we're trying to rewrite this improper fraction into this mixed fraction. Right. So the way that we do that, well, 23 copies of 18 go into this 427. So we have 427. We can then subtract off 23 copies of 18, and we have a remainder of 13. Okay, so we end up with, is that right? Yes, that is right. Okay, so we end up with 13 over 18, and I should probably say these are all in degrees. Degrees. Okay. Yeah. Maybe I can just comment off to the side what it was that this is. So I did 427. I guess we can use this old school version of divide. Okay, and what we found is that this is actually 23 remainder. I think that's the notation. Remainder 13. Okay. So maybe you remember that from like elementary school. Really old kind of thing, right? So this is like a converting this improper fraction into a mixed fraction. The whole number of parts, the whole copies of 18, that's the, what's that called? Quotient? And then the remainder is the parts left over, the parts where you don't have a full copy of 18 to put together into one whole part of the pie or whatever. Fractions. Okay. So that's fine. And then what we need to do is, well, this is the fractional part. We need to multiply this by this conversion factor, 60 minutes. So that is now going to convert this into minutes, this whole thing into minutes. Let me try to also color code this a little bit. All right, so whatever that is, let's see, what happens to the denominator? 60 divided by 18. Okay, so there's some simplification, but not completely. Let me think. So you can divide out 6. Okay, we can cancel out 6, and we're going to be left with 10 on top. Okay, so let me see. We have 10 on top, we have 3 on the bottom, and that does not simplify. So I'm just going to copy this. So 23, we're just copying that part, and then plus, so now this is 13 times 10, so 130 over 3, and now this is in minutes. This is already departing from my previous solutions, but let's just make sure everything is okay. All right, so this decimal is still the same as that decimal, so I think we're good. And so we have a whole part and we have a fractional part. So we can write this as 43 minutes plus some number of minutes over 3. We have now a fractional portion. And so our goal is now to write this 130 over 3, this fraction, from the improper fraction that it is into a mixed fraction. So we would just, well, when we do the division, this is our quotient. We need to find the remainder. Well, 130, then we subtract off 43 copies of 3. We're left with 1. And maybe you could have guessed that because you see that the decimal portion is just 3 repeated. Maybe you can recall that 1/3 is 0.3 repeating. Okay, so we have this, and then we multiply this by 60 to convert it to seconds. And then, of course, that's going to give me 20. So maybe I can just say that's equal to 20 seconds. So you see that we end up getting the same thing. We just did it 2 different ways. We found the 23 degrees over here. We found the 43 minutes there, and then we found the 20 seconds at the very end. And yeah, same answer. Okay. Well, this one's a bit more long-winded, but what do I want to say? Well, if you're dividing by 7, then you're going to have a lot in the bar, or like if you're dividing by 19 or some other prime number, like that. So there are instances perhaps where working with the fractions will be easier on you than working with a decimal. I mean, but then again, if you can use answer, it's kind of always easier to use the calculator, I guess. Yeah. Oh well. Okay. Number 4. So we have that secant of theta is equal to 7, and theta is some acute angle. That's just because the acute angle part just tells us that we're working in the first quadrant, essentially. We want to find the exact values, and okay, exact here is important. So I know that a lot of people rounded for this problem, and that's not good. Okay, if it asks you for exact values, you have to give an exact value, which means you can't round, you can't truncate your decimal. If it's asking for exact, it has to be exact. Like, I don't know what to say about that. Like, this is still a truncated value. If you have 3 bar, then that is exact, but it's easier to just say this is a third, for example. And I'm guessing with this one, we're going to have square root somewhere. Okay, well, let's see. How do we go about this kind of problem? Well, the idea is that this trig equation, it corresponds to a specific triangle, and we do this by drawing the triangle. So, secant theta is equal to 7. Well, what does that tell us about the triangle? Well, so the way we go about this, secant, in fact, all of the trig functions are ratios of sides of the triangle. And so, maybe I should recall this. So, this is a definitional thing. So, sine is defined to be the opposite side over the hypotenuse. Cosine is defined to be the adjacent side over the hypotenuse. Tangent is defined to be opposite over adjacent. And then you have the other 3 trig functions, which are just reciprocals. So if you can remember the pairing of the function with its reciprocal, then you're good to go. And so the pairing is like this. So this is cotangent. So tan and cotan are reciprocals. Cosine and secant are reciprocals. Sine and cosecant are reciprocals. So going from this column to this column, we just have to flip the fraction. And when we do this problem, we're going to have our answers all be in fractions, represented as fractions. Okay, so, right, so secant is going to be hypotenuse over adjacent. So, and we're viewing this 7 as 7 over 1. So what makes sense is that we can just kind of correspond these values. So hypotenuse we can set to be 7, and adjacent side we can be set to be 1. I'm marking also that this is my angle that I'm referring everything to, so that's why this side is the adjacent side. It matters what angle you choose to refer to your perspective to be. And pretty much I'm always going to draw my triangles in this format, like aligned like this rather than like this. I know a lot of people, they seem to prefer drawing it like this. The reason that I'm not drawing this triangle is because this triangle actually lives in the second quadrant, whereas this one lives in the first quadrant. We'll talk about that probably before the second exam. Yeah. So I'm going to erase that. Okay. Right, so the idea is that this triangle represents this trig equation. Okay. So like if you actually created this triangle out of sticks, like real world sticks, and you measure this angle, it would be precisely the thing that you would need to then plug into secant to then get 7. Or if you could do inverse secant on a calculator, the measure of the angle would line up with the real world construction. Like this triangle is going to give you, it's going to correspond to this equation. That's kind of the method here. Okay. Now to answer a lot of this problem, I'm going to need this side. This is called the opposite side. So the way we do that is, well, we have a right triangle, so we're going to use the Pythagorean theorem. So the Pythagorean theorem says, just in case, I think one person did not use Pythagorean theorem. So it says that the legs squared, the sum of the legs squared, I should say, just sum of legs squared is equal to hypotenuse squared. So that means that, well, if I call this guy b, then 1 squared plus b squared is going to equal 7 squared. Okay, now notice that when we solve for b, we're going to subtract this over, and then we're going to take the square root. So we end up getting the equation b is equal to the square root of 7 squared minus 1 squared. I know that some people are kind of, they've kind of gotten used to a pattern which kind of breaks here. Okay, so when you are calculating one of the sides, you have a square root and you have to square things, but you don't always add, right? So in this case in particular, because we're solving for the a leg rather than the hypotenuse, we end up subtracting the squared values instead of adding them. So you have to kind of be aware of what you're solving for. But if you use the original statement of Pythagorean theorem, you're not going to go wrong with that. Right. So, okay. Now we go ahead and calculate this. That's 49 minus 1, so we get 48 in a square root. If you're okay with simplifying this, well, we can think about what's the biggest square number that we can pull out of this. So I see that there's 4 in here, but I'm pretty sure that you can pull more out. I think you can pull 16 out. Let's see if 16 divides perfectly. Yes. Yes. So I know one person had a question on this. So the way this works is we've just found that 48 is actually 16 times 3. And we have a square root over that. And so we can then end up square rooting the 16, which will give me a 4 outside of any square root. And then we have root 3 still. Okay, so this is simplifying the radical that I've just done. Square root of 48 is the same as 4 radical 3. All right, you can use either format. I'm going to use 4 radical 3. Okay, so then answering this question, well, I'm just going to first put this value into my triangle so I can just stare at this triangle and then fill in all of the values. I'm going to go ahead and erase this. Oh no. Erase this. And maybe we can also, yeah. Right, so sine of theta is, well, it's opposite over hypotenuse. So opposite side over hypotenuse. So we get 4 radical 3 over 7. Cosine is adjacent over hypotenuse. This is adjacent is 1, hypotenuse is 7. Tangent, opposite over adjacent, so opposite over adjacent. That's 4 radical 3 over 1. You wouldn't need to put the 1, you could just say 4 radical 3. Cosecant is the reciprocal, so I don't need to look at the triangle anymore. I can just take this fraction and flip numerator and denominator. So 7 over 4 radical 3. Flip this, well actually this is given to us, so we knew that to begin with. And then cotangent, 1 over 4 root 3. So these are the values that we need for our answer. One other thing I should say, there is another approach we can do for this problem, because Nagi has given you guys tons of formulas, so I don't have them in front of me, but I can pull them up and maybe paste them in. I don't like those formulas, but one can work with those to actually do this calculation. It's just, the formulas actually come from looking at the triangle, so it's a little bit silly. Well, maybe I can just show them in the recording. So, yeah. So, you're given... What are you given? Maybe this is not the right one. Oh yeah, something like this, isn't it? Probably. I don't know. I saw one person like do it algebraically, and I was just like, why? Why would you do that? I have no idea which one it is. Maybe it's this one. Maybe it's this one. I don't know. This recording is getting kind of long. Do I care to do this? I mean, I think that the visual way of doing it is far more intuitive. Let's see. He definitely talked through a problem that's like this on his slides. Like, there was an exercise. There was definitely an exercise. I mean, I'll do it. I'll just do it as an exercise, and if you don't care, then you can skip ahead in the recording. So so pretending that we didn't know any of these values, well, except like maybe secant. Can I scroll? Why is this not letting me scroll? I wanna panning hand. Okay, that's great. Alright, so what do we know? We know secant of theta is equal to 7. That's all we know. Well, because of the reciprocal property, we know that secant and cosine are reciprocal, so we can then immediately say cosine theta is 1 over 7. Great. Then what? Well, then we would probably use one of the Pythagorean identities. Yeah, so you're given... Okay, I'm going to print screen this. This is probably going to work. Okay, so copy, paste. Right. So it's like you would need this cheat sheet. Right. Because right. No, so because theta is an acute angle, it's kind of an assumption in our problem. Right there. The plus minus we can ignore. That's because in the other quadrants, so in the first quadrant, all of the trig functions, and we really only need to talk about sine, cosine, and tangent, all of them are plus here. Sine, cosine, and tangent are all plus here. But in the other quadrants, one of them is going to be negative for each one. I think there's like a mnemonic, but I can never remember the mnemonic. Okay, maybe I'll just talk about this. So sine is actually going to be positive here and here. It's negative here and there. Cosine is actually positive in this quadrant and this quadrant, negative there. Tangent is checkerboard, plus, minus, minus. So this is how the trig functions behave on the unit circle. Yeah, and so it's just kind of nice when we are restricted to the first quadrant because all of these guys are positive. But when we work in the other quadrants, then we have to think about what the trig function, what its sign should be. That's what the plus minus means. Think about what the whether the value should be positive or minus for the given quadrant that you're in. So it's, yeah. Okay. That's kind of a preview ahead. But okay, so cosine, we have cosine. The immediate thing that I know is that you can calculate sine from cosine. It's actually from, I don't like this formula. The thing to remember, or I mean, we'll get to it eventually, is, oh no, sine squared plus cosine squared equals 1. We have this identity. And then when you solve this guy, that's how you get the first two equations. Okay, and that's why I have the plus minus. Oh, it's because you end up taking a square root. But so here, let's see, we can then deduce what sine theta should be. It should be the positive root of 1 minus 1 over 7 squared. Right, so that is 1 minus 1 over 49, the square root. That's going to be 48 over 49, the square root, which, 9, that's a 9. And so that's going to be square root of 48 over 7, which simplifies. And we can just check that that is actually the same answer. So sine, yes. Yeah, so for radical 3, that is square root of 48 from this calculation here. Okay, so we got the same value for sine. And I'm pretty sure how we do the rest is just, like reciprocal properties. Once you have these, you can actually start using a ton of the other formulas, like what he calls the ratio identity and the product identities. So that's great. I would probably never use the ratio identities or the product identities. Probably. You just need to know that sine over cosine is tangent. That's like the only thing you need to know. Which, I mean, we may as well just use that now. Well, there's two ways to calculate tangent from here. We could do sine over cosine, or we could do this formula. I'll just do sine over cosine. So tangent is the sine over cosine, and that's 48 over 7. That's the sine value. Cosine is 1 over 7. How do we simplify this complex fraction? Well, easiest way to think about this, multiply top and bottom by 7. That's going to cancel the denominators in both parts. And so you end up with the value 48, or root 48, don't you? Yeah. Okay, great. So we end up with, we get this guy, we get this guy. We have sine. It's kind of piecing together a bunch of random puzzles. Yeah, so that is the same as radical 48. Okay. If I reciprocate tangent, I get cotangent. Yeah. So yeah, cotangent, that's what he calls the, what does he call it? Reciprocal identities. Okay, sure. Reciprocal identities. Cotangent theta is equal to 1 over the tangent of theta. So we know this is 1 over root 48. Okay, great. We found another guy. Let's see. What are we missing? Secant. 1, 2, 3, 4, 5. Okay. Sine, cosine, tangent, secant, and cosecant. We're missing cosecant. Cosecant is reciprocal of sine. Right. So cosecant is reciprocal of sine. We know what sine is. It's this guy. Root 48 over 7, which, of course, why would you write that? You just automatically flip that fraction. There we go. Okay. Yeah, so yeah, doing it algebraically is just you're juggling a ton of formulas. It is very non-systematic, I would say. Whereas geometrically, like drawing the triangle that corresponds to the equation is very straightforward. You just draw the triangle, find the missing side, and then just put side lengths over side lengths, and then you get all the values. Of course, it matters that you actually draw the triangle correctly, put the sides in the right places. I think that a number of people did make mistakes with this by putting 1 on the opposite instead of the adjacent. So you do need to pay attention to what the trig function is that you're given, and then to put the values into the right places. Right, so maybe just to emphasize this again. So secant is reciprocal of cosine. So it's cosine is adjacent over hypotenuse, which means secant is hypotenuse over adjacent. So when we have our 7 over 1, 7 goes to hypotenuse, 1 goes to adjacent. We really always want to put our theta here, and so adjacent is this side. Okay. I wonder, maybe the reason a lot of people made this mistake is actually because the practice exam had a different function. Yeah, yes. Wait, no, is this the same? Cosecant. Yeah. So the practice exam had cosecant, which is reciprocal of cosine. So you would have put the value given. You would have put the 1 on this. Right. So looking at what trig function you're given, that matters. Don't over pattern yourself to the practice, because then you're like, you should understand what can vary. So the function can vary, the trig function can vary, the numbers can vary. You should understand the process, the procedure kind of completely without memorizing specifically for cosecant, or not cosecant, cosecant, what is being done. Because yeah, a lot of people, they just did not understand switching from cosecant to secant. Things change a little bit. Okay. This is gonna be like over an hour. Oh man. Okay. Come on. My computer's being a bit slow. Oh no. Alright, hopefully it's still fine, but this is being janky. Oh no, I should not. Ah. Okay, well, whatever. Okay. Right, 5, 6. Alright, so number 5, we have a triangle ABC. C is our 90-degree angle. So the first issue that people had with this problem was setting up their triangle incorrectly. Like they didn't label things correctly. It comes down to what's given to you. So with a problem like this, you're gonna be told a 90-degree angle, and that 90-degree angle has to go where the 90-degree angle is in your diagram. Okay, so C has to go here. Okay. Then your other angle, in this case, we have the angle A and we have the opposite side A. So these two are opposite each other in our triangle. This is the convention for our notation. When we have an arbitrary triangle, the convention that we're using is that the angle and the opposite side will have the same letter, just different cases. So if this is angle B, then the opposite side is going to be little b. If this is the angle C, opposite side is little c. That's how we set up our labeling so that we don't confuse ourselves too much. Okay, so angle A and side little a are going to be opposite each other. In this case, we can put the angle in either place. It doesn't matter, so I'm just going to put it down here, 35 degrees. And so little a is going to be on this side, and it's 4 centimeters. Filling in the rest, this has to be angle B. This has to be side C. This has to be side B. Okay. So to solve our triangle, that means we need to get all of the other values, all the values that are missing. Okay. The easiest value to get here is going to be this angle B, right? So this is a right triangle, which means that the other two angles, apart from the right angle, are going to add to 90 degrees. So we know that, how do I want to put it? I guess we could say angle A plus angle B in this case are going to equal 90 degrees. So I can solve for the angle B. Okay, we just do 90 degrees minus the 35 degrees that we're given. That is 55 degrees. Okay. Where are we? Okay, good. Yes. Next, we try to solve the sides. So let's focus on side B first. So side B, the way I've been explaining this is to try to relate this in terms of the things we're given. So I want to compare, I want to think about these three things: the angle A, and then these two sides. So with respect to this angle, this guy is the opposite side. This guy is the hypotenuse. And so you have to think what trig function relates opposite, or not hypotenuse, did I say hypotenuse? Opposite and adjacent. Sorry, I'm tired. Opposite and adjacent. So you have to think which trig function relates these two. Well, tangent is going to be the guy that does this. So let me undo those highlights. So tangent is the function we want to consider, and so we need to write now the full equation. So tangent of the angle in this case is 35 degrees, is going to be opposite side, which we know what that is. That's 4 centimeters, over the adjacent side, which is B. Okay, so we know this equation must hold true. And now that gives us a way to find the length of B. We just solve for B in this equation. Tangent 35, 4 is just a number, tangent, that's just a number. We'll end up calculating it in a bit. So we solve for that. Just multiply both sides by B, divide both sides by tan 35 degrees, and you end up getting this 4 over tangent 35 degrees. And whatever number this is, it's going to be measured in centimeters, because in our problems, length is measured in terms of centimeters, so all of our lengths are going to be in terms of centimeters. Okay, so now we go ahead and plug this into our calculator, and we get 5.71259 centimeters. I'm going to round that to the nearest 0.01. So this is approximately 5.71 centimeters. Okay. Okay, box this guy. Right. And then the last one is we need to figure out C. So let's think about this again. We want to relate the givens to the thing we're solving for. So we have this angle, we have the opposite side, we have the hypotenuse. Opposite, hypotenuse, you should think of sine. So our trig function is going to be sine in this case. So we say sine of the angle, 35 degrees, is going to be opposite over hypotenuse. There's a little thing there, I don't want that there. Okay, well, that's great. All right, so yeah, we have this equation. And then, maybe I can put that below just to match things up. Okay, so now multiply by c, divide by sine of 35 degrees. We end up with the equation c equals 4 over sine 35 degrees. And we go ahead and plug that into our calculator. It's going to be a length measured in centimeters. Great. Okay, so we end up with 6.97 centimeters. Yeah, and that matches what I did previously. Great. Number 6. How many more problems are there? There's like, oh man, I took way too long with the other ones. Okay, so this one, a lot of people made the mistake of following the practice exam too closely. So on the practice, it asked you to find the area of the sector, but here it's asking you to find the length of the arc, right? So you should just draw a quick little sketch of the situation here, right? The area would be this whole region. The length would just be this part that I'm trying to shade in blue. Maybe I can shade this in red instead. So this would be area, and the formula you should have them written down. I guess if you can have it memorized, that would be great. But if you don't have it memorized, 1/2. Wait, is it 1/2? What am I doing? I'm writing random stuff. It should be radius squared theta, I think. Let me think. Okay, so the way I had to do this, I have to reconstruct it. So for a full circle, we have 2 pi as our theta, but pi r squared is supposed to be pi r squared, right? Yeah, pi r squared is supposed to be area of a circle, so we need a 1/2 factor in front. Okay, so this is the formula for the area of a sector, where this is our theta. Okay, and then for the length, arc length is going to be r times theta. And you can check that by if you had 2 pi as the full circle, then this formula gives us 2 pi r, which is the circumference, the formula for the circumference of a circle. So that's right. Okay. Right, so on the practice, you would have worked with this formula in red, but for this problem on the midterm exam, you were supposed to use the formula in blue. Let's see. So we have 83 degrees as our central angle. Okay, so theta is 83 degrees. Now, one thing you need to know, very important about these formulas, these work in radians. So theta must be in radians. They must be in radians. Double exclamation. Okay, so if you did this in degrees, you'd be off by a factor. So we have to convert this into radians. So we divide by 180 degrees, multiply by pi. That's going to cancel the degrees. We're going to be left with something in radians. And this doesn't simplify. 83 is, it might actually be prime. At the very least, it doesn't share any factors with 180. So we're left with this as our angle measure, and we're also told the circle has a diameter of 12. Well, a diameter, I did have to mention this to someone. So this is the diameter, this whole length is the diameter. The radius is half of the diameter. So this part would be the radius. I don't want to write this on top like that. Undo. Yeah, there we go. Yeah, so that's the radius. So to get the radius, we have to divide by 2. So the radius is just going to be 6. And this is in inches. Okay. Right, so then arc length, L, is equal to r theta, which is going to be 6 times 83 pi over 180. We see a bit of cancellation. Yeah, so we can cancel that, and the cancellation is going to give me 30 in the denominator. So we end up with 83 pi over 30. This is a valid answer. Well, okay, I should add units. Once I add units, it's a valid answer. Inches, right? Inches. Because the problem is stated in terms of inches. If you wrote centimeters, this I would take a point off because I'm a bit picky with units, making sure that the units are correct. Okay, yeah, so 83 pi over 30, that's one valid answer. The other, it would be, okay, so this, where's my cursor? So this corresponds to the answering it as a fraction of pi. Answering it as a decimal, that's if you just plug this value into your calculator. On this calculator, pi is the value for pi, so there we go. It also implicitly knows I'm multiplying. All right, so this is approximately 8.6, 2.1. Okay, so 8.69 inches. So you could say either of these would be accepted. Okay. Number 7, acute angle is with this. So this is a trig equation, just like whatever the previous problem was, this guy. Yeah, just like this problem, I would want to create the triangle that corresponds to this trig equation. In this case, the angle is called alpha, so I'm just going to mark this as alpha. Tangent is opposite over adjacent, so 8 should be my opposite side, 15 should be my adjacent side. And then I'm left trying to figure out what the hypotenuse side is. Well, Pythagorean Theorem says that whatever this value is, I don't know, I'm question mark. Okay, so 15 squared plus 8 squared is equal to question mark squared. You solve this equation, you end up with question mark is equal to, I'm going to erase question mark in a minute. Maybe I shouldn't have called it that. Oh, whatever. 15 squared plus 8 squared. Okay. And for this, I would need a calculator. Well, I don't really need a calculator. I can do this. 2, is it 2? 225. Should be 225 plus 64 in a square root. 290. That's weird. Can't be 294. That's not a perfect square. There's something wrong. 15 squared is 225. That's a 4. I can't read. 460. Wait, something is wrong, isn't it? Oh, no, maybe it is. Maybe it is that. Hold on. Is it? No. 289. 6 plus 2 is 8. Wow. incredible. 289 square root. Okay, so now this I can see this is a perfect square. It's 17. All right, so square root of 289 gives me 17. You know how to do that on a calculator. Right, so this is 17. Great. And we're only asked to find the sine and the cosine of the angle. Okay, so we can then just figure out sine and cosine in this triangle. All right, so according to the triangle, sine is going to be the opposite side over hypotenuse. Opposite is 8, hypotenuse is 17, so we get that. And then cosine is adjacent over hypotenuse. So 15 over 17. That's all we need to do. Can just go ahead and box it. If you were to try avoid doing this graphically, well, you could use the Pythagorean identity to get secant, then reciprocate it to get cosine. Don't know if there's an easier way to get anything. I'm just gonna leave it in this way. Like there is a way you can do this algebraically without drawing anything, but I think this is clear. Okay. Last problem. So we want to solve a triangle. We're given two lengths. We're given a right angle. So we start off with, well, we need to make sure that our labeling is correct. That's the important thing that I think a lot of people made mistakes on. So this guy, we know, must be the angle that we call B. And we have little b. So we know that where this has to go, this has to be the opposite side to the angle. And then A, 5 centimeters. Well, this can be in either place. I guess we can put A, let me try to make it match my solution so I don't have to think. So, not think as much. So, okay, I'm going to put A on this side. You could put it on the other side. It's okay either way. So we have, then this is the angle A, this is the angle C, this is the side C. Express angle in degrees, round to the nearest 0.01, solve. All right, so the first thing I would solve for is the missing side. So we would use the Pythagorean Theorem. You can manipulate it and you'll end up getting 11 squared minus 5 squared. I guess I'll explain over here how we do that. So we know that 5 squared plus c squared, and this is 5. Make this look like a 5. 5 squared plus c squared is equal to 11 squared. That's what Pythagorean theorem says. Then you subtract over the 5 squared, take a square root, that will solve for c. That's how we get this. And this doesn't simplify, or, well, this isn't a perfect square, so we end up with 96. 121 minus 25 is 96, okay. Root 96. You can probably pull multiple copies of 3. Let's see, 96 divided by, oh no. 96 divided by 3. Oh, multiple copies of 2, okay. 96 over 4, 24. Okay, so I can divide by 16 actually. All right, so we have that this is actually equal to 16 times 6, which means that this is, in reduced form, this is 4 radical 6. I suppose just in case someone wrote this, in decimal, I can also just calculate the decimal. 4 squared root 6. So this is approximately 9 point. So we have to round this to the nearest 0.1. You see, this is going to round up to 0.80. And I'm going to place that 0 there to emphasize that this actually is to the precision that we're asked for. Okay. Next, let's try to solve for the side C. Let me see. Okay, I'm gonna highlight the givens, which are these two guys. So we're gonna try to set things up using these two sides, not using the side that we derived. Okay, so angle C. I want a trig expression, or I want a trig equation that involves these sides and C. So, well, from the perspective of angle C, this is the adjacent side, this is the hypotenuse. Adjacent and hypotenuse should make you think of cosine. So cosine of this angle is, we know, adjacent over hypotenuse. 5/11. Now we take the inverse cosine of both sides of this equation, and that's going to give me C is, well, I'm going to need to then plug this into a calculator. Inverse cosine of 5/11. So my little calculator here. On this calculator, cosine is actually called arc cosine. So 5/11. And it's important that this is in degrees. So that's just checking that again, that is the case. Right, so approximately 62.96 degrees. All right. And the last thing I want or need is the angle A. So we want to figure out the angle A in terms of these two given sides. Well, now with respect to A, right, looking from the perspective of angle A, this is still hypotenuse, but this is actually opposite now. So we have the opposite side, we have the hypotenuse. That should make you think of sine. Okay, so the equation that we end up getting is sine of the angle A is opposite side over hypotenuse. Okay, now taking inverse sine of both sides of this equation, we get this, inverse sine of 5/11. Plugging this into my calculator, arc sine of 5/11. No, go away. Why does it do that? We get 27.04. I have to round up. 0.4. Oh no. Degrees. Yes, and that matches. So I'm just going to box these last values. Wait, what is this? I can't be right. Okay, this is 9.80. How did that erase things? 9.80 centimeters. I should specify centimeters because units are given. All right, so red box. So this guy. Oh man. This angle and this angle. These are the three things that I needed to solve for to finish off this problem. All right, and that's all of midterm 1.